Okay, lastly, I want to quickly show you what you need to do for the purity ratio. So for the purity ratio, there are three different things that you need to give me. The first one is the 260 to 230 ratio. The second one is 260 to 280 ratio, and the third one is just the value of the 320 by itself. Now remember, for each one of these values, you want to subtract the blanks from them before you give me those ratios. So for the first one, I want to go ahead and do that. So I will show you minus the blank up here, and then I want to divide that by the 230. Now here the top is my 230. I want to take the 230 from up there and subtract the 230 blank, so 0.139, and I get a number. Well, for 260 to 230, my ratio should be 2.0 or higher, and it is, so that's good. Now the next one is going to be my 260 to 280 ratio, so I'm going to do the same exact thing. I'm going to go ahead and first do the 260, take away 0.057, and then I'm going to divide that by now my 280. So 280 is the one right underneath it, so I'm going to go ahead and take the blank of 280, and I get 1.82. For a pure DNA sample, that 260 to 280 ratio should be 1.8. So I did pretty good over there as well. And then lastly, you just want to write your A through 320 value by itself. The A320 value should be close to 0. The closer it is to 0, the less insoluble light scattering material is there. Again, remember to blank it. So I take my 320 value from the same ratio that I used, and then I take away my 320 millicu, and there I am. Now I have my sample right there. So if I look at these numbers, I will see that these numbers are my purity ratios. This is going to tell me about my carbohydrate phenol component of the fraction, so how much contamination from those I have. This is my protein, and this is my insoluble matter. Now, while we are here, I want to actually remind you of something I forgot to do in the last video in my hurry. I apologize for that. So this is the concentration of your DNA in that diluted, 1/2 diluted fraction. That's not your actual concentration. So you actually need to first get the correct concentration here. And to do that, you have to multiply with the dilution factor. And the dilution factor here was 2, so you want to multiply by 2, because this was my 50% DNA sample. So the actual concentration is actually going to be the number that you had gotten equals this number multiplied by dilution factor, in this case 2. That's the actual concentration of my DNA, not the 0.1062, and I apologize that I did not say that in the first video. And again, for the second one, then obviously this number is going to be multiplied by 2 as well. So it's 212.4 microgram per mil. If I had a milliliter of this solution, I would have 212 microgram of DNA in there. My experimental is also going to be now different because it should be twice as much. So it's 26.55 microgram of DNA. That would be in there. Now, if you were to look at the sheet again, what is the concentration of your DNA? Here it asks you, it actually gives you the conversion factor as microliter, and so you can put that number here. So the answer to this one is going to be this number right here, 0.2124 microgram per microliter, and that's what you would have put here, 0.2124 microgram per microliter. And then based on this, what is the experimental yield is going to be my 20 something that I just got, 26.55 micrograms of DNA, 26.55 micrograms of DNA. And then the relative percent difference you would do accordingly. Now again, I used an imaginary number here, so all this stuff is incorrect. It's not exactly what you would be getting. So obviously the RPD calculation is not going to be correct. However, you would do the same thing, that you'll do the absolute difference between the experimental and the theoretical value divided by the average of the two multiplied by 100%. That it gives you the actual RPD of your sample. With the RNA, you are going to do the same thing, except this time you are using the tri-reagent, so you may be getting more cells out or whatever, and you're going to use the range of RNA that you expect to see in a mammalian cell. It's between 10 to 30 picogram per cell, so you can use the average at 15 picogram to make use of that. The conversion factor for RNA is that for an absorbance of 1, you have 40 microgram per 1,000 microliter concentration of RNA, sorry, apologize. So make sure that you're using the right conversion factors for the right thing. And also make sure that you take into account the dilution factor, which I had forgotten to do in the last video. So make sure that you take into account that value as well. So here it is. Hopefully this is helpful. Hopefully I didn't confuse you more, and hopefully this will help you get your assignment taken care of. If you have further questions, you can email me, or for those of you who are in the Monday section, you can ask me any questions you may have tomorrow morning and turn in the assignment later in the day. Take care. Bye.